Hi, welcome back. So today I think I would like to do something a little bit. I'd like to do a little bit of jump to page 17. Okay, around that area where we look at instead of as we go in sequence. If we go in sequence, we'll be talking about stagnation and static pressure. But instead, I think I can talk about atmospheric pressure first. Okay. Um, some of you may have gone to the petrol kiosk to pump your pressure of for your car or your bicycle tire, right? So what you usually do is in front of that pump kiosk, you will press your number, right, to a certain setting. Say, I think for car tires, usually you put 230 psi. That is pounds per square inch, which is a pressure, and then you just plug in this holes into your car tire, and what happens is that the tire will be inflated, okay, with a certain pressure inside the tire. So this pressure, right, this additional pressure is basically what is shown on the display, which is 230 psi. Okay, it is a pressure that is extra, that is higher than your normal atmospheric pressure, because you realize that everything in the world is being acted on by atmospheric pressure. So when you inflate, you're inflating something higher. Okay, and this pressure, this higher pressure, is our gauge pressure. Okay, that's why there's this gauge. This is a gauge number. So this 230 is a gauge pressure, and what you have inside the tire is literally your absolute pressure. Okay, absolute pressure is equals to atmospheric pressure plus your gauge pressure. Okay, so take for example, if I'm inflating 10 kilopascal into the tire, so my P gauge is equals to 10 kilopascal, and your atmospheric pressure is usually 101 kilopascal. So my absolute pressure will become 10 plus 101, which is 111 kilopascals. Okay, so this absolute pressure is higher than the atmospheric pressure, and you can see that from page 17 in the diagram, showing that the amount that is higher than atmospheric is your gauge pressure, anything that is above. Okay, which brings us to the next topic, right? Vacuum pressure. Well, you can add air into the vessel, you can also take air out. For example, I think nowadays there are these containers in the market where you are able to put a manual hand pump, right? And then you pull up and down, and this device just sucks the air out, okay, out of the container. So by sucking the air out of the container, right, your pressure inside, right, is actually less than atmospheric pressure. Okay, how much less? Okay, it is how much less is your vacuum pressure. Okay, again, figure 1-4 over here indicates this. For example, if this suction device pulls out a vacuum pressure of 10 kilopascal. Okay, originally the container has a atmospheric pressure of 101 kilopascal. So the absolute pressure inside this container now will become 101 minus 10. Okay, therefore it is 91 kilopascal. So the absolute pressure turns out to be lower than the atmospheric pressure, okay, by this amount, a vacuum pressure of 10 kilopascal. So anytime you see a vacuum pressure, you need to deduct it from the atmospheric pressure, right? So that's it for these three types of pressure: absolute, atmospheric, and gauge. Okay, and they form a single equation which you can remember. Okay. There is another equation, okay, which I'm going to talk about now, which is related more to moving flows. Okay, so that is actually on page 13. So we are jumping back to page 13. So here we see pressure in a fluid motion, topic 1.4.2. Okay, it basically every time if you see a question that involves flows in motion, okay, then we are talking about this equation. Stagnation pressure is equals to static pressure plus your dynamic pressure. Okay, stagnation pressure is also known as total pressure. So it is the static component and the dynamic component. Okay, usually when we say a certain flow has a certain pressure, right? For example, a certain pipe flow has a pressure of 30 kilopascal. Okay, so this pressure is the static pressure. Okay, so this pressure is the static pressure. And then the question will say that there is a certain speed. Okay, let's say a certain speed of 2 meters per second. Okay, and if the flow is you need to know what kind of fluid is the flow. If it is a wind, then the fluid is air. Okay, if let's say if it is a river, then the fluid of course is water. Okay, maybe the sometimes pipe flow, right, will involve oil. So it really depends on what fluid you're talking about. And these two is what will affect your dynamic pressure, because dynamic pressure is your half density times speed square. Okay, so this density, right, is the density of the flow. Okay, whatever fluid it is, you use the density of the fluid that is flowing. So for example, if I'm talking about oil at 2 meters per second, then I will put, let's say oil has 900 kilogram per meter cube. Okay, so the dynamic pressure will be half times 900 times 2 square. Okay, so the answer is 1800 Pascal. Okay, so the dynamic pressure is 1800 pascals. So for example, if we have this dynamic pressure with this static pressure, your stagnation or total pressure will be equals to 30 kilopascal plus 1800 pascal, which gives you 31.8 kilopascal total pressure. This is the total pressure. Okay, so this is when we are dealing with fluid in motion, then you look at this particular equation. Okay. Next video, I will go through a very simple example to cap this.